Hello, I'm going to talk about hitting weighted even cycles in planar graphs. This is work done with collaborators Alexander and Matthias from the Hamburg University of Technology and with my supervisor at the University of Waterloo. In the feedback vertex set problem, we're given a graph with cost CV on the vertices, and we're going to output a set S of vertices of minimum cost that intersects every cycle. Here, these two shaded gray nodes form a feasible feedback vertex set. Variations on this include directed FVS, where we only want to hit directed cycles, and subset FVS, where we're only interested in hitting the cycles that go through a specific set of vertices. But another natural variation is to look at parity restrictions, even cycle transversal and odd cycle transversal, where we're only interested in hitting the even, respectively, odd cycles of our graph. So in the even cycle transversal problem, you have a graph G, cost CV, and when the output is set S of vertices of minimum cost that intersects every even cycle. Okay. We'll say cycles C1 and C2 cross if the enclosed areas do. So here, C1 bounds this region, C2 bounds this region, and the two regions, neither which contains the other, and they overlap. We will say a set script C is uncrossable if for any crossing pair C1 and C2, we can find another pair of cycles C1 prime, C2 prime that do not cross and they use the same set of vertices. So here, in our top figure, C1 and C2 cross because they overlap in this area. In the middle figure, the areas that the red cycle bound and that the black cycle bound are disjoint. And therefore, C1 prime and C2 prime do not cross. In the bottom figure, the region bounded by C2 prime is contained in the region bounded by C1 prime. And therefore, the two cycles in the bottom figure also do not cross. So Berman and Yaroslav, 2012, showed that planar uncrossable FVS is 2.4 approximal. So why even cycle transversal? There's been much recent work involving parity constraints in optimization. Lokshanov, Ramanujan, Sarab, and Zahavi, 2020, talk about the parameterized complexity of odd cycle transversal. Lokshanov, Ramanujan, 2012, study multi-way cut with parity constraints. And Misera, Ramanujan, Sarab study parameterized algorithms for even cycle transversal, and many more. Another reason is that even cycles are not uncrossable. So we need to extend the Berman-Yaroslav 2012 framework, and this is a natural kind of this is a natural variation that does not satisfy uncrossability. Graphs without even cycles also have tree width 2, so even cycle transversal could be used as a subroutine in the tree width vertex deletion problem. So the way we'll formulate is we'll formulate the natural LP, which has a variable xv for all vertices v, and we set xv to be 1 if v is in our hitting set, and xv to be 0 otherwise. So our objective is to minimize the weight of our hitting set, subject to that we have at least one node on every even cycle. And our main result is that this natural LP has an integrality gap of 47/7 in planar graphs. So we will show this using the primal dual method. So just to refresh your memory, in the primal dual method, we start with the zero dual solution, empty hitting set. And while G minus S contains an even cycle, we increase the dual variables YC as much as possible in some given set C prime. We maintain dual feasibility. And when a dual constraint is satisfied with equality, we add the corresponding vertex to our hitting set. And at the end, we reverse delete. That is, we consider all the nodes in the reverse order that we added them, and we try to delete them if possible. It's a folklore result that if for variables YC that we incremented, C intersects at most alpha hit nodes on average, then we have an alpha approximation. We will say that the dual variable YC pays for the number of hit nodes on C. So here the cycle C is paying for these 3 hit nodes. Let us consider a naive algorithm for even cycle transversal, and that is just to extend the face minimal idea of Berman-Yalotsev. Here in this figure, we have an odd number of these length 5 faces, and the bottom path has odd length. So therefore, this face F is even, and it looks like a candidate that we could try to increase. So let's suppose we increase YF. What happens? Well, for each of these blue nodes, the corresponding dual constraint will become satisfied with equality. So we end up picking each of these blue nodes into our hitting set. And then we go to reverse deletion, and we can delete so that we have only one blue node per face of length 5. But we must keep one blue node per face of length 5, because if we do not, we can take a path where for every face of length 5, we go through the red vertex, except for the one where none of the blue vertices are selected. And then we go around and go through the bottom path, and this highlighted cycle will be even. So therefore, we need to keep at least one blue node per face of length 5. Well, that's not a very good solution, because I can pick one blue node, one red node, which is much cheaper. So let's see how we deal with this. So simple case, let's suppose our graph contains an even cycle where only 2 nodes have outside neighbors. I'm going to increment its corresponding dual variable. And why do that? Well, we can show that any minimal hitting set S will contain at most 2 nodes of such a cycle C. For instance, if we pick these 4 nodes, then I can delete, for instance, these. I can delete everything except for these 2 nodes here. And likewise, you can convince yourself that whatever you start with, you can always delete until you have at most 2 nodes. So let us assume that our graph G does not contain such an even cycle. And we want to simplify our graph. So we'll do, well, an induced path will contain at most 2 hit nodes. So let us contract long induced path. So here, this path here gets contracted into this edge here. This path here gets contracted into this edge here, and so forth. And now I'm going to continue a bit. And when I have these parallel edges, I'm going to replace them with a single edge, which I call twin. And the point is that this twin edge has whatever parity you want it to be. So any cycle that uses a twin edge, we should say it's even. And I'm just going to contract any remaining vertices of degree 2. So here we are able to take this complicated gadget and replace it with just an edge like this. Yeah. The second ingredient of analysis is this thing called tiling. So we want to cover our graph with even cycles. And we'll show that when we do this, the average such cycle has few hit nodes. So we'll define a tiling as a set of non-overlapping even cycles, each bounding 1 or 2 faces. So here on the left, I have the graph. On the right, I have this cycle here at the even face. I have this cycle that bounds the light blue region, this cycle that bounds the green region, this cycle that bounds the black region, and this cycle that bounds the gray region, and they form a tiling. Notice that they do not overlap. We can show that 2/3 of the finite faces of our graph can be covered by some tiling script M. In essence, there's a small caveat. So now let me describe the algorithm. We start with, as in primal dual, with the 0 dual solution, empty hitting set. And while G minus S contains an even cycle, I first compress the graph. Next, I find a large tiling script M. And then I just increment the corresponding dual variable. And when a node becomes tight, I add it to our hitting set. And lastly, I perform a reverse deletion. So for the analysis, note that a cycle that covers 2 faces, F1 and F2, pays at most the number of hit nodes that are either on F1 or on F2. So here I have a cycle of length 4, and I can say, well, the cycle pays at most the number of hit nodes are either on F1, so these 3 nodes, or on F2, these 3 nodes. So I bound the amount the cycle pays for by 6 in this case, which is an upper bound, and that's okay. So the total amount our dual variables pay for is you sum over all cycles of our tiling, and the amount you sum over is the number of hit nodes on that cycle. As mentioned before, for a cycle that contains 2 phases, the amount it pays for is at most the number of hit nodes that are on either face. So you can think of it as we break that cycle into two cycles, into its 2 faces. Each of those 2 faces pays for the number of hit nodes that are on that face. So next, I'm going to bound this total dual payment by just the number, sum over all faces, the number of hit nodes that are on the face. So recall that when we defined a tiling, we said that they do not overlap. So when I break a cycle up into its 2 faces, I never get a face twice. So for instance, here I break up this blue cycle into these 2 smaller light blue and dark blue cycles. I break up this green cycle into this face and this face. And when I do that, I never get a face counted more than once. So I can bound the total dual payment by summing over all, but a summation over all faces of our graph. And for each face, I just count the number of hit nodes on that face. Also recall that because we cover 2/3 the total number of 2/3 of all faces, the number of cycles of our tiling is at least 1/3 times the total number of faces of our graph. So now we want to bound how many hit nodes a face of our graph hits on average. And for that, we use Berman-Yalovtsev's result for a subset FES, which if you look into the details, it basically says, if you have a minimal hitting set, faces of your graph do not hit too many hit nodes. So the total dual payment is now bounded by, in particular, they hit at most 18/7 hit nodes on average. So the total dual payment is now bounded by 18/7 times the total number of faces of our graph. And from the fact that the number of cycles of our tiling is at least 1/3 times the total number of faces, we're able to bound the total dual payment by 54/7 times the number of cycles of our tiling. And by standard primal dual arguments, that shows that this algorithm is a 54/7 approximation. And using a bit more work, we can get the approximation bound down to 47/7. Okay, so let me talk about why large tilings exist. So tilings are matchings and even faces, but let's just pay attention to the matchings for now. By Tutt's theorem, if there is no large matching, then there exists a witness set X such that when I remove X, the graph has many odd components. So here, it's a matching on the dual. So the dual graph delete X has many odd components, and we will basically end up showing that this X being very small and the number of odd components being very large violates Euler's formula for planar graphs. And that will be that's how we will conclude that there cannot be the set X and therefore a large matching exists. So I talked about even cycle transversal as a natural variation of the feedback vertex set problem. So in the algorithm, we computed a 2 compression. And then we found a large tiling. We incremented the corresponding dual variables. And why is this good? Well, the dual variable YC pays for the number of hit nodes on C. And recall that for cycles over tiling, they consist of 2 faces. So we ended up showing that the average face has few hit nodes. And that put together completes the analysis. And an open question we have is, can we improve the approximation bound? So I didn't get into too much of the details on where the bound comes from, but one place we can think about incrementing is I gave a bound of 2/3 where we can say we can cover 2/3 the number of faces. And then I also said that the average face hits at most 18/7 hit nodes. But one question is, can those sort of somehow bad cases, that's you're only able to cover 2/3 and an average face hits 18/7 hit nodes, can they occur together? Or is it possible that you only have sort of one bad outcome and you can improve a little bit? So here is a link to our paper on arXiv. Thank you for your attention.